So I think we'll go ahead and get started. And we're excited today to have our virtual speaker, Dr. Dimitri Azar, which I think many of you already know as our former dean. Before I actually introduce him, I wanted to just make a couple comments about our ITIM track. So, which is the Innovation in Technology and Internal Medicine program, which we started 2 years ago. And we had 3 brave residents volunteer at that time, and now we had 11 more this year. So it's a very exciting program. And the motivation was basically that there's a lot of changes coming to medicine and based on things like huge data, artificial intelligence, robotics, intellectual property, venture capital. And the idea was to expose the residents to many of these ideas. And we've done everything from having boot camps and R coding to seminars like today. So with that, I'd like to introduce our speaker for today, Dr. Dimitri Azar, who is currently the Senior Director of Ophthalmic Innovation at Verily Life Sciences. He originally received his MD in medicine and ophthalmologic training at Beirut University, American University in Beirut, and then moved to Massachusetts Eye and Ear at Harvard Medical School, where he eventually became chief resident and a faculty member. And then we all know him as our dean. He's has numerous accomplishments, which I'll just summarize by saying he has over 500 peer-reviewed publications. He has current NIH funding. And I forgot to say, he also has a MBA, which he obtained while he was here with high honors from the University of Chicago Blue School. And with that, I think I'll turn it over to Dr. Azar. So welcome.
Thank you so
back
much.
To your old stomping grounds.
This is great. I really am honored. And,
I can't hear you.
I am. Do you hear me now? Are you able to hear me? I'm seeing some thumbs up, so it means people are hearing me. Okay. I am truly honored to be here. Let me share screen from my side here, if that's okay.
Okay.
Let's see if we can do that. Share screen, and then this is the PowerPoint. That click allow. Let's see. Do you see my screen here or no?
Yes.
And I just wanna thank everybody for this opportunity. I have to start that it took me some time to think about when David and I spoke about the topic. I told him I have to give an ophthalmological perspective of this convergence of AI, microelectronics, and clinical medicine. And we named the talk From Milli to Micro to Nano. And one other thing, David, that happened in August, I'm sorry I didn't give you that, is that Verily and Google spun off an ophthalmological company that I'm now leading, and we called it 2020 Therapeutics. So that's included here. As we do with all talks, we have to acknowledge potential conflicts of interest. Soon I will not include the board of directors because I stepped down from these activities, being on the board of Novartis and Verb Surgical. And now I'm leading the 2020 Therapeutics, and I'm on the advisory board for Alphabet Verily. But the important point here is that I am discussing, given the various roles I've had, just my own personal opinions. I'm not discussing those of any other entity that I'm affiliated with. I like to go back to the time that I was Dean of the College of Medicine, and we all know about the triple goals of medicine, of education, research, and clinical care. But I think now we're facing this new concept of convergence. You probably, some of you may see the STEM written here, the STEM sciences. And they're allowing us to do many, many important things when you combine medicine on the one hand and engineering and data science on the other. Hence the word convergence. And in ophthalmology, you can see here an illustration of this convergence that we are talking about. And since that 1910 famous Flexner report in medicine, I think that we've gone through 3 new revolutions, and intentionally using the word revolution here rather than evolution. Think about the discovery of the structure of the DNA in the 50s, and then the molecular biology revolution that happened with it. This is shown in green, followed by the genomics revolution with the Human Genome Project and all the new things that can happen in medicine. But now I think we're going in the 21st century into convergence of artificial intelligence and microelectronics with clinical medicine. This brings us back to what Sir William Osler had said: medicine is art based on science. I've been invited to give many, many talks on artificial intelligence in ophthalmology and outside ophthalmology. And there will be speakers before me and after me who are talking about artificial intelligence. So I had to put a false quote by Sir William Osler that says, not all problems will be solved by artificial intelligence. We still have to work as doctors and treat patients and take care of them. But artificial intelligence, despite the hype, is one other tool that will enable us to do our jobs better. So in the College of Medicine, when we discussed this idea of convergence of engineering, AI, and data science, we can see benefits. It contributes to the excellence in clinical care, broadens the impact and scope of medicine. And I don't know if people are able to see my pointer, but this convergence here on one side is a new pillar, I think, in many colleges of medicine. For sure, the College of Medicine, University of Illinois College of Medicine, that adds more support to the foundation of clinical care, education, and research. But I think if we don't add a 5th column, which is humanism, we may lose something because of the fear of everything becoming now machine related. And this is an important thing. I just put a picture of some of the faculty of the College of Medicine in the Miles Square facility, for example, here. And they want to order an X-ray. In the good old days, they take the X-ray. It's read by a radiologist here, and then sends a report, and it's done. Now the system has changed, as you all know. Enter the cloud, the AI programs. So what would happen is that the test is done, images taken in the facility, it goes to the AI program, then the radiologist would concur. I mean, here we chose a very distinguished interventional radiologist, but still they would concur. And then this information goes back to the referring physician, goes back to the facility. But I think the most important element that we as physicians are not paying attention to, but it's important, is that there's input now from the facility, from the data that's obtained after the X-ray is taken, going to the program, and the program is learning on an ongoing basis so that the next radiological image that is evaluated will be evaluated more intelligently, hence the word artificial intelligence. And this convergence goes global. I can give you an example in areas in Africa where there is no water, barely any electricity, and in the past you needed to go to check a retina, you needed to have the healthcare provider bring their gasoline generator, backup generator, tug along a $25,000 camera in order to take an image of the optic nerve like this. In today's world now, and this is happening as we speak, an iPhone attachment can be used to check vision, to take an image of the optic nerve. It is powered by a solarly powered. The guy goes on a bike, goes to multiple places, is seeing patients here. The image is sent to a reading center in Nairobi, for example, could be in England or in the US. And then the information live is then provided, and that person who needs cataract surgery or needs to have their retina checked or sugar checked will then be told by the healthcare provider on the spot, giving the information. So you're getting the good intelligence, and that could have gone to a cloud and the data collected. I mentioned the humanistic pillar as being one that's important because we can talk about all these futuristic things, microelectronics, artificial intelligence, and lest we forget about our patient, we need to remember that the reason we went into the medicine field, medical fields in the beginning, is to take care of patients. So compassion cannot be overstated. In fact, I'm reminded by, some of you know that I'm an opera fan, by Amfortis's words in Wagner's Parsifal, durch Mitleid Wissen, which means through compassion, knowledge. Compassion and knowledge don't go in opposite directions. They are reinforcing each other. Professionalism, another aspect. And we have to be, we're talking about medical students or residents and fellows. This was taken for granted, but in the new world, we have to re-emphasize this, give courses, make sure that that's part of our curriculum, not just the hidden curriculum, but the explicit curriculum. Ways of communication properly between colleagues and with patients and with other stakeholders. Working as teams. Gone are the days when one person could make all the decisions and be a superstar. It's going to be the star is the team and helping those most in need. These are basic, but I think we cannot forget them, and we need to be explicit about making them part of a pillar to counterbalance the computer assisted work that we are needing more and more, whether it's in our EHRs or in our interpretation of data. And then talking about data, we have to be responsible and make sure that if the data belongs to the patients and the fact that the patients cannot access it easily, we have to make sure that we do everything we can to give the information to the patient. And you can imagine in the brave new world that we are facing, these can be done via computers, but it's important that as physicians, as trainees, as people who are being trained or are training others, we don't forget this element. Having said that, we can, it's not a surprise that many of you have noticed that in the 20th century, only 2 decades ago and earlier, we used to have big rooms dedicated in hospitals, in clinics, to having huge devices, big devices, that at the end gave you a reading, and we needed to know normal or abnormal to tell the patient you need something to do or not. The world is changing now and going from these big sophisticated devices, and I'm giving you examples from the ophthalmological field here of lasers and topographers and wavefront analyzers, addressing either the afferent or the efferent arc, moving from those to smaller devices and microelectronics. And that is not unique to ophthalmology. I thought I'll pepper my talk here with some medical slides. We are now realizing that our patients are seeing us for a short period of time. Could be 10, 15-minute visit, and then they are away for 6 months, 3 months, or a year. So what happens outside that visit is clouding, or maybe clouding our understanding. And we need to remove that cloud and understand what's happening outside that short period here in the middle that the patient is seeing us. And we may find out much more serious problems that perchance did not get detected during the visit. And second, most importantly, they may have happened 2 or 3 months earlier, and we are only dealing with them if detected at the visit long after the onset of the disease. So you can imagine that cloud connectivity is going to offer us a lot of data in multi-dimensions that can be seen individually or tied together. Of course, my focus is on this part, the intraocular pressure, but you can see the metabolic data, the kinetic data going up, downstairs, cardiac data, and Apple Watch can give you an EKG and so on. So this data, it's already complex when you're looking at one aspect of it, but when you're combining it, there's a richness of information that can be tied in time and location to allow us to understand what's happening to the patient well in advance of coming to their regularly scheduled visit. But this is only possible because of our now ability to handle huge data and create small devices and connecting these to the cloud. And many of you probably have heard a lot about artificial intelligence. I was talking to the editor of the JAMA at an ophthalmology meeting he attended because of the big AI things. And we had a conversation about the number of articles that he's receiving on a regular basis that say that AI is better than doctors in this particular area, etc. And he reached a stage to say, we're not going to be worried about that. We need to know, what is AI teaching us? And much of the information now is not coming from the small microelectronic devices because there may be no need for them in some fields, or they may be difficult to get these devices in other fields. But the point that I want to emphasize, it's not just about AI, it is hardware. Hardware is catching up to the nanometer scale. And that's what led to the title of this talk. So we have to remember that miniaturization gives us a lot of opportunities, no doubt, but also they come with challenges. We have to think about the computational elements, the form factors. They have to be powered somehow, so there have to be batteries, and we're able now to miniaturize batteries. The pumps that may be needed can also be miniaturized, also to the micro and nano scales. And then all these electronics, if you're inserting them in implants inside the body, in my particular area, it's inside the eye, we have to find ways of protecting them so they can stay in place for a long period of time. And the inflection point for technology is that when this miniaturization is guided by the medical profession. So this is one of the models that we are now employing in the eye. As you know, the eye is unique here because of the limited space. Tiny small areas where you can't put a big device. It's not like skin or other parts of the body. The real estate is very, very precious and limited. And so we've come up with many solutions where you can have external coins that communicate with devices in the tissue. This could be your cornea, your anterior chamber, or any other part of the body. And there could be sensors that are connected to these ASICs and switches. And then there is a power supply, antenna, and connectors. And all of these are fitting in an area that is measured in a few millimeters in at least the ophthalmological side. That system we've tested in multiple things. And yesterday, Verily sent an announcement about the prototype lens, which includes, this is one of my earlier patents from about 15 years ago. We've added a lot of these. We're now in excess of 40 patents in this field. And this is drawing, that's not an actual lens. That the actual lens has not been revealed, but this is a picture that came from the company that shows that there could be a tiny sensor in your contact lens. By the way, these devices could be on or in the eye, not necessarily implantable all the time. And this is made to address a problem of presbyopia. This is a problem of the lens becoming less flexible as we get older. And after age 45, our ability to read at near unaided becomes limited. And many of us would need reading glasses like I'm doing now. And this accommodating contact lens will allow for on-demand dynamic focus. And it includes a hybrid lens And the research that we've done and experimentations have yielded a fully functional prototype with the existing advances in the optic quality, in the fit, comfort, and in manufacturing repeatability. 5 years of work has led to this prototype lens that consists of an electroactive liquid crystal, which was described in my original patent, shown here, and encased in a custom developed rigid gas permeable material, and then wrapped within a soft silicone hydrogel skirt. And small clinical studies with working functional lenses demonstrated that this dynamic accommodating contact lens provides wearers with better visual acuity than comparable multifocal contact lenses. I'm reading from the press release that happened yesterday. So I'm very excited about that. And just to give you the microelectronic aspects, this is a pin here you see on the left-hand side. And in this tiny little tip, one of the engineers who's working with me now at 2020 designed this ASIC. It is, if you include the electronic components, about 600 microns. The thickness is about 200 microns. 200 microns, the thickness of 2 pieces of paper. And this has 50 million circuits inside it. And that can sit, for example, in a contact lens, like I said earlier, or it could go into devices that are very, very tiny, that the eye will not have a serious reaction to them. You may say it's a waste to put this under the skin, because you can put under the skin something that is less sophisticated. But I'm sure in the future, this will go from the eye to other non-ophthalmological applications. In addition to these sensing and power transmission capabilities, we are moving into pumps that can pump fluid, various fluids, from being this huge device to something that is called a millipump. And the research in this area is mind-boggling. We're also going into things that are at the nanoscale. This pump follows Archimedes' principle of rotating a cylinder here, which is called a screw, with a certain 1 nanometer pitch of the screw, and it can move liquids and other gels from one compartment to another. We have not used this one, but this is one of the things we considered in the past to be able to give us a nanoscale pumping. Many of these applications are in the lab, but I can see that with the proper material and proper testing, they can go into patients. But you can put all this technology together to find at the end that the enemies of engineers, called Na+, Cl-, and H2O, which we see a lot of in the body environment, are coming to mess up our electronics. All the engineers I work with, and I'm very fortunate to have a large number of really talented engineers. I mean, smarter than, twice as smart as I am, and they're afraid of sodium, they're afraid of chlorine. And we are very happy. We know that biology is all sodium, chlorine, and H2O, to mention just a few. So we've come up with a system which is called multi-layer barriers. I can't tell you much more, but it's kind of slowing down the movement of sodium, chlorine, other ions, and water to go from the body environment above to the circuitry down below. And we can simulate these in the lab, and we've determined that we can slow down the entrance before the devices become non-functional in the order of 10 to 20 years. And hopefully in the future, we'll be able to do this. And by the way, this can be done in a way that these barriers are not, we're not talking about titanium hermetically sealed boxes. This is a transparent medium that is covered by that material, allowing the light to go through it, but not these other molecules. And in medicine, the focus has been so far, as you can see from this graph, from a paper from a few years ago, it's mostly diagnostic imaging. It's about more than 3/4 of the applications of artificial intelligence. But this electrodiagnosis is starting to grow, and we see a big area of artificial intelligence slash microelectronic applications coming to the front right now. And the data that's generated is so huge that in the past we couldn't handle it. That the non-neural network approaches in the past were, it's shown in green here on the left-hand side, were superior to the neural network applications. But in today's world, all these other approaches, the non-artificial intelligence approaches and non-neural network, deep learning, are reaching a plateau because the neural networks require more data, provide more data, can analyze more data, and there's no limit to our ability to harness that data. And this is not just applicable today to ophthalmology, other fields such as radiology, pathology, dermatology. One thing in common between these and ophthalmology is that there's a lot of descriptive diagnostics in these, and there's a big role for artificial intelligence convergence with microelectronics to help in the clinical care of patients. They can help us identify which patient should be referred for management and care. They can improve our efficiency. It can be used, you don't need now these huge, big computers to be done on a smartphone, and can improve and promote personalized medicine and recognize disease-specific patterns, and can correlate novel features to give us innovative scientific insights. And there are many AI learning algorithms for this group. I mean, in some other venues, I would go step by step about all the AI systems, even though the one that we like to focus on in our field is deep learning convolutional neural network, shown in the penultimate line here. But there are examples of unsupervised, such as clustering, shown here, where you're essentially the computer, the program randomly chooses 2 points and then tries to identify the centroid, and with multiple iterations, ultimately it ends up sorting out the 2 clusters that you can see here. Other programs include, you know, all about linear regression analysis, whether it's 2D on the left or 3D on the right, logistic regression analysis, and the nearest neighbor system. These are systems used a lot in business schools. But for a long time, support vector machines used to be the backbone of artificial intelligence studies, and the early literature in the field where this used to be the predominant, let's call it workhorse. The random forest around, I mean, this is something I learned when I was taking my business degree, and it's something that still many predictive algorithms for businesses depend on this approach. But the most important one is neural networks, convolutional neural networks. I'm going to spend a little time on this just to explain it for those who know what I'm talking about. I apologize for oversimplification here. But imagine we want to look at this retinal image that is taken by that field worker in sub-Saharan Africa, or in the fanciest clinic in Chicago. And we're looking at 3 different features in it. And then the computer over time has allocated a weight, W1 or W2 or W3, W4 for each feature. And then from those, we identify some intermediate features. And ultimately, based on this, an output is made, is given. And that output is that this is normal. Okay, suppose we did that. But then we have human intelligent observers, and they say, no, 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 there's an abnormality here. We need to reclassify this. That information then is fed into the program, and the program, as a result of that, will change all these weights, the little W's you see here, you know, millions of them in hidden layers, until ultimately it will make sure that all the previous images are correctly labeled, as well as the one that was incorrectly labeled here. So in essence, as training commences, neural networks start off without any fine-tuning and return random results, and progressively learns the combinations and permutations of important features. And as opposed to human beings, they have an ability to forget easily. They learn to ignore the unimportant features in order to make the diagnosis. So to summarize this again, there are two pathways: the forward propagation that I was talking about initially. An output is generated, an error is calculated, and then there's backward back propagation in order to improve the weighting algorithm that would allow us to improve the program with time. So as more and more data is collected, the program is learning at the cost of consuming more data. And that system is not much different, it seems, than the learning system that we have had for our neurons. Again, these can be shown mathematically. Many of you may feel this is too complicated, but in essence, there's a summation operator and an activation function that are included inside every hidden and every output node that we're getting there, so that the program will get to the outcomes that we are desiring. And so some people show this as a simple network where there's only one hidden layer, or when you have multiple, sometimes thousands or hundreds of these hidden layers shown in yellow here before an output is provided. And that becomes a problem for some people, because you can't go back and study the program and say, how did they arrive at that answer? There's an element of faith, so to speak here, that it is looking at these outputs without knowing exactly how the computer arrived at the program. I mean, if you want to look at hundreds of thousands of millions of lines of code, you will know exactly how they arrived at it, but it becomes difficult to interpret to another person what the computer practically has done. I generated this graph last year, but now with the COVID, I did not update it. But this was a 2.5-year period of multiple diseases where AI has been applied in the eye. And I'm going to elaborate a little bit more. This 2.5-year period by far exceeded the 5-year periods that you see before. And I predict that now I couldn't do it because the number of papers have grown exponentially in this area. Similarly, at the meetings, we can see in blue, in orange is the 2018, 2019. I was hoping to update for this for 2020, but the meeting was canceled due to COVID. So these applications, at least in ophthalmology, fall into two categories: diagnosis and screening, which has been taken the lion's share of all the applications, and then the discovery. I'm more interested in this. In this diagnosis and screening tells us about the potential capabilities of AI, especially when it's applied to microelectronics. But the discovery can tell us a little bit more about deepening our understanding of the disease. So let's start with this, and an area of corneal topography, for example. Many of you may be familiar with Scheimpflug imaging. This is an old-fashioned camera that was, designed, devised, and patented by an Austrian army officer more than 100 years ago, where you actually tilt the lens plane relative to the film plane, so that if you have a subject plane, say this is a field, you can see the distance from the lens varies here, but by changing these angles and make them meet at what is known as the Scheimpflug line, everything on this subject plane will be on focus of the film by having that element. Now we have autofocus, so we don't have these focused but distorted images that are generated. But this principle has been applied to the cornea, because you have the device very close to the cornea and the distance is varying, and you're able to get multiple images that diagnose patients with keratoconus, or if any of you is considering LASIK surgery, there may be abnormalities in the cornea that prevent you, that will make LASIK very risky for you, and you may end up having bad results from LASIK. So the way around it is to use this gold standard for diagnosis of corneal irregularities. Time will not allow me to go in more detail about this. But for use at home or without having this pachymetric measurement, we can look at reflections just coming out of the cornea. Think of it as a convex mirror. And then we can identify patients who have normal, suspect, or advanced disease based on these images. And we have done work and came up with a classification that sorted out all these diseases. But it wasn't as good, because what we applied was a 10-layer artificial intelligence component, 10 different subgroups in the vertical line. And I think in the future, we will be able to look at these images and be able to match the gold standard by having a one-to-one match and making an artificial intelligence program. And many groups are working on this problem this time. And with microelectronics, this could be part of your watch or part of your phone camera or part of many of the devices that we are working on. Glaucoma is a very serious disease. It's a silent disease. People lose their peripheral field slowly. The optic nerve fibers get affected due to the high pressure in the eye. And the pressure is higher than the nerve, what the nerve fiber layer can tolerate inside the eye. So you end up having a phenomenon shown here as cupping. You see, this is the cup here. Usually it should be 30% of the size of the disc, the optic disc, but here this is approaching 80%, and some areas it has gone completely. This is advanced glaucoma. Everybody will know that looking at the eye. But this patient at some point, 10 years earlier or 15 years earlier, may have had a normally appearing disc. It's a very slowly progressive disease. And so there are many methodologies now of looking at glaucoma patients. And at UIC, the group led by Dr. Halak has been pioneering in trying to find multiple data sources for these patients and connecting them into one system that would allow researching that data and finding ways of predicting who of the patients who are starting with a slightly abnormal disc will actually progress to have disease and who will not. And that takes into consideration collecting data from multiple big devices that are led into that small program that then will be able to differentiate disease. And as you all know, the visual field will get smaller and smaller in these patients, that ultimately they will have a central field also. And that's called tunnel vision. That is characteristic of many of the patients who have that disease. So of course, there are multiple different ways of looking at this. And the idea is that we can label these images and obtain them through small devices, rather than spending an hour in the office collecting all this data. That can be done at home in the near future, hopefully. And perhaps the biggest area where AI has taken off in ophthalmology is in fundus photography for retinal disease. This is one sampling of all the possible retinal diseases that you can see, and this is taken through a very large field called Optus device. And this is a diagram that was generated by that company showing, for example, a retinal detachment, circinate exudates at the optic disc, cottonwool spots, a hemangioma, etc. I know many of you have heard these terms in medicine, but won't you like to have a patient come into your office, put their eye, and a picture is taken, and then a display in front of you shows all of these with a label already in white colored, like I have in front of you? That is not too far into the future, that any doctor, you don't have to be a retinal specialist, you don't have to be an ophthalmologist, a patient may be able to take a picture of their eye and it comes labeled. And that's the power of this combination of these microelectronics and artificial intelligence. Of course, this will happen only after multiple research groups who are being very, very active since roughly 2015. So over the past 5 years, the work has been amazing. Here's an example of some of the work happening at Stanford, and they have been collaborators with the UIC team on much of this work. And the best demonstration of this potential was in 2016 in that JAMA article shown here. I mean, if you want to read about something, I'm going to keep this in front of you. JAMA 2016, December 13. Here are the pages, 2366 to 2368. This program, for the first time, and this was published by the Google group, was able to show that that they were able to diagnose diabetic retinopathy and subclassify it with better sensitivity and specificity than most eye doctors, and as good as some of the retinal specialists. And this paper was so influential that when JAMA looked at the top 10 papers of the decade, meaning from 2010 to 2019, the 2016 had two papers, Barack Obama's paper on healthcare and this JAMA paper, plus 8 others that I forgot what they are. But this work now has been duplicated, and the FDA has approved devices based on the same kind of work that now you can imagine somebody, after you diagnose somebody with diabetic retinopathy, you tell them, go get a visit to see your eye doctors. They go to see the eye doctor. The eye doctor says, yeah, I'm not a retinal specialist. I see something. They send them to a retinal specialist. By that time, they've lost 3 days of work and they are at risk of being fired. So they decide not to come back again, especially if it turns out to be normal. Now they don't have to do this. It could be in your office or at the phlebotomist. They're coming to check their hemoglobin A1C. They look into this device undilated. They don't need to dilate the pupils. The image is taken, the AI program takes a minute or two and sends a response. You need to see an eye doctor immediately, the retinal specialist, you will act quickly. Or they say, come back for another image, which is the majority of patients, in a year. So now you will make sure that the retinal specialists are not seeing normal patients all day long who have been referred to them, but they're seeing the disease, the eyes with serious disease that they can take care of, or the ones that have a risk of developing disease. And the normal patients, the people with normal retinas who have diabetes, can be assured that they don't need to be examined. They come on a routine and get this test done on a routine basis. And I think this has been, this is one of the biggest impacts of artificial intelligence in ophthalmology. Other things can happen with macular degeneration. This is a blinding disease, especially in the elderly in the Western world and now growing in third world countries. And we give these patients injections of anti-VEGF to slow down the progression of the disease. But there are some patients with intermediate disease where you don't know whether they will reach a stage of having exudative disease. And now we can look at these eyes, and through artificial intelligence programs led by the group in Vienna by Dr. Schmidt-Erfurth, Ursula, and she has demonstrated that now we can understand the disease better. Finally, the group at Moorfields in England, working with DeepMind at Google, have found out that you could they solve the problem of the OCT approach in ophthalmology, where there are millions and millions of data points that can be very, very difficult to evaluate. It would take hours to differentiate one retina from another because you're scanning every little point and connecting it. So what they did, they found a solution that they also published in Nature Medicine, again, one of the seminal papers in December 2017. And what they did is they did what is known as segmentation. And based on that, they were able to identify 37 different diseases in the eye. And of course, these were labeled correctly by a team of experts. And then what they did is they calculated that the error rate was 5.5%. That's this line that I'm pointing to in this graph here, taken from their paper in 2017. And then they got some retinal specialists shown on the middle panels, and some retinal optometrists. There are retinal optometrists in England who could do that. And then they identified the error rate. You can see the retinal optometrists, for the most part, did not do as well as the device. Here, we're not deciding, does the patient have diabetic retinopathy or not? We're showing a picture, and the program is saying the diagnosis is the following: one of 37 different diagnoses. Has not been approved by the FDA. It's still in the research phase. And you can see that maybe the retinal specialists, for the most part, especially if they also gained access to the fundus images and to the notes about that patient, they did about the same. I mean, it was within the margin of error when you compare to the 5.5 error. So that tells us that the potential of going now to diagnosis is also very, very, very high, especially when it comes to complicated diseases with the appropriate technology called OCT. So now we've covered, so let me see where we are on time. I have a few more minutes here to talk about discovery aspect. Diagnosis and screening, it's huge. Discovery, we're still behind. I'll give you an example of that by looking at dry eye. For example, I mean, many of you may have dry eye. Many of our patients have dry eye. And I was part of a group called the DUSE-2, where we published a report, more than 200 pages, about how to diagnose properly dry eye and subclassify the dry eye into aqueous deficient dry eye or evaporative dry eye, and looking at various factors that can be, by taking all these tests that I'm showing you here. This thing may take an hour to tell somebody you have dry eye. And you fill these questionnaires, including the DEQ5 and the OSDI questionnaires. And from these, you do some, take osmolarity, etc. I'm sending this quickly. You do some measurements. And at the end, you end up with this very rigorous approach of telling somebody you have dry eye, and it's the evaporative type. But that takes too much to come up with something. I mean, yeah, we wrote the papers. It's great. But could there be something else that can give us something better? So I asked my retina colleagues, what do you do to diagnose dry eye? And they said, we ask the patient, do you have dry eye? They don't do any of this stuff because they're busy looking at retinas. So essentially, we have a problem of either overcomplication done by the cornea specialists, such as myself and my colleagues, or oversimplification, just ask the patient. So could we use these data and come up with an algorithm by using microelectronics and artificial intelligence to do that? And we have an ongoing collaboration between our group on the industry side, 2020, and with UIC to try to solve this problem. Also, we can learn, for example, the refractive error prediction. As you know, when you go to your doctor, they don't look at your retina to calculate your refractive error. But if you feed data of numbers of the power, the error in the glasses, that's called the refractive error, and the pictures of the fundus of the eye, the program can do good associations, and they can predict to within half a diopter in certain instances, or 1 diopter. And this came from the UK Biobank and the ARID study of macular degeneration. And from that data, you can start looking at the back of the eye and ask the program, what did you look at to make you diagnose this patient as being a -6.6 diopter myope? And you can see things that doctors have never looked at before in the back of the eye. And we are spending a lot of time now looking at these attention maps that are the hidden layer that the program learned over time and started making predictions based on something we were not aware even existed before. Similarly, for predicting cardiovascular risk factors from retinal fundus images. This paper was published 2 years ago in Nature Biomedical Engineering. I'm sure many of you are aware of that. A lot of data, but they looked at these patients and they were able to identify cardiovascular risk factors, including age, gender, smoking, etc. And it's interesting to take the same approach and learn and ask, what was the program looking at to predict with accuracy the age of the patient? Here's an example of somebody's age who was 57.6, and the program predicted, just by looking at this colored image, that this is coming from a 59.1-year-old. Again, knowing the gender with great accuracy. You can see knowing age is based on the vessels in the retina. And knowing the gender is some reflective area coming from the center of the fovea. Well, knowing whether somebody is a smoker or not. Determining hemoglobin A1C, determining BMI, etc., etc. So by looking at the retina, when you have a patient coming in, I can imagine this device being available in a cardiologist's office or an endocrinologist or general practitioner's office to really get more insight without taking any blood studies. So I'm reaching the end here, so I'd like to summarize. You will all agree with me, I hope, that the world is now moving towards the milli, micro, and even the nanoscale. There's great convergence between the microelectronics, and the going into miniaturization. And there is a shift to the form factors that would allow microfabrication and the batteries. I didn't discuss the batteries in detail, but these batteries in the future are going to be foldable, solid state, and can be easily recharged. And this conformal coatings that would allow the body elements, all the electrolytes, not to interfere with the electronics, and would allow a lot of technologies, especially when coupled with artificial intelligence. But there are limitations, including the quality and diversity of the training sets. For example, the Google group found out that when they did the study on the Americans for diabetic retinopathy and went to India, they had to increase the number to roughly 1 million images to be able to cover the various diverse populations that between African American, people of Indian descent, the Indian subcontinent, and white Europeans and American. Problems with the sensor data quality. Also, if you have poor sensor, either immediately or later, can be a problem. And then these programs, no matter how smart they are, they're only making a statistical prediction and they may make errors. And if we depend a lot of these, we are at risk of, for our medical students, our residents, our fellows, as they get engaged more into this engineering aspect, to forget about what got us into medicine. And we have to realize that this knowledge is only a foundation to facilitate interpretation of data. And we cannot overemphasize the importance of the humanistic elements of medicine that I mentioned earlier. Also, there are lots of regulatory burdens. If this is a learning system, there's the FDA freezing it before requiring to be frozen and stop learning before it gets approved. What if it starts learning bad habits after it gets approved? And I mentioned the black box dilemma and fear of the unknown. And I think that's legitimate, both on the patient and the doctor. So we must ensure that AI will be a helpful tool rather than a competitor for early referrals and easy diagnosis. We must ensure that the sensor data is linked longitudinally with integrity and without potential data abuse. Because if I give my data for these various researchers or companies who are collecting the data to learn to have predictive power, we don't want my data, if I don't give permission, to be used or abused. So there's a risk there, of course. I thank you so much for your attention, and I'm happy to take questions. David, do you want me to answer any questions?
I'm sorry, I was muted. Can you see the chat?
Yeah, I see. Oh, so you want me to look at the chat? Okay, great. Dr. Kundus asks, what happened here? Dr. Kundus disappeared. But he asked, I like the cardiovascular part. I put that especially for you, George.
Dimitri, it's interesting, but using CT, we can calculate the actual age of the patient. Like you said, based on their vascular age, we can guess their age, too, rather than their actual age.
Exactly. So, I mean, we're going to find out there are many things that predict age. But I think there's a good way of knowing somebody's age. You ask them about a date of birth, or you look at your ID.
Never tell the truth.
Well, thank you so much for your kind comments, George. And it's so nice to see you. I hope everybody is doing well. I mean, I see the names of so many good friends here. And I am so happy to be sharing this talk with you. But Dr. Patricia Finn is asking, what's your advice for the next generation?
Dimitri, can I just say thank you so much. We're so excited to see you. There are many other comments that are actually asking that, many of our house staff, our chief residents, everybody, just what's your advice as you're thinking about it? And they've articulated much better than I. So I just speak the voice for them.
I have to tell you, for those who came into medicine and hated the fact that quantitative aspects were downplayed, now you can rejoice. There's an opportunity to apply your mathematical skills into those who do not. You don't have to know what's going on. The program will give you the diagnosis. So, but it would allow for opportunities for research that are very exciting for people who love the mathematical aspects. Second, I think, and more importantly, is from us, the people who are teaching the students and the residents and fellows. We have to give them these opportunities, let them ask questions and provide the resources. And what you are doing now, Patricia and David, is really outstanding. It's giving people a glimpse, an opportunity to go into this, the convergence of engineering and data science, etc. But also we cannot do that at the risk of the basic principles of professionalism, compassion, etc. In the past, you couldn't teach this because I would say, well, it's of course we have to do it. But now I think it has to be part of the formal curriculum. We can't take it for granted. Yep. If the person is spending all their day at the computer, even after COVID, that's how they're dealing with the patient. It's very difficult to not to emphasize the basic things. You know, I used to say shaking hands is important. Now we say don't shake hands for COVID. But I can tell you an example. I had a resident who was seeing a patient with me, and I was waiting outside and filled the whole chart and went outside with the printout. In the ophthalmology at that time, we had a printout and an electronic thing. So I was reading and telling and so on, and I said, hey, the patient's name is Chris. Is that a male or female? Had the resident looked at me with total, I was ashamed, couldn't remember whether it was a male or female. Why? Because they went in, it was a dark room, checked the eyes, sat down, typed, checked something else, and at some point developed a scotoma of whether they were dealing with a woman or a man. And I went in, put the lights on, you know, very attractive woman in the room, the patient. And the resident could not remember that. And she happened to come with the name Chris, so it allowed for that opportunity. I know, but it was a good lesson to pay attention, to shake hands, to talk to the patient, rather than look at whatever organ of interest they're examining. Sorry, here I see Dr. Prabhakar next. How do PIs at academic medical center initiate projects or are required to work with leading companies? Not at all. Like Google, for example, the programs they've developed are shared completely with everybody. In fact, they lost in some certain areas the competitiveness for products because it's open source. Anybody can go in, get it, and use it. And at UIC in ophthalmology, there are at least 4 or 5 researchers who are working on company-generated stuff and using them. The key question in research is not the capabilities of these products. It is, what is the research question? Something that this can allow us to do things better. Thank you, Prab, for this question. It's so nice to see you and hear from you.
Yeah, thank you, Dimitri, as always. Terrific presentation, very inspiring.
Thank you. Let me see. I am going down the list. We have time, right, to go a few more minutes?
So any thoughts on enhancing the humanistic pillar?
I think this has been established, well known, and hopefully you don't need a computer to tell you how to exercise your humanistic pillar. Some doctors, when I emphasized the humanistic pillar in one of the meetings, said, oh, so you want us to be nurses? I said, yes, you have, if a nurse takes care of a patient, they are doing part of the care that the doctor should be doing as well. But the two are not mutually exclusive. They should be mutually reinforcing. Let me see here. Some other people ask questions. I can hear Fionn. I don't know. This was okay. DJ Jarsania, thank you. And then Kevin Chi, same thing. Julianne, Amy Jorgensen, thank you for sharing. Well, it's my honor and pleasure. And then what were the most important things? This came from Samer Habil. Important things that you've done throughout medical school that helped you go where you are. Well, what I did is I started formulating as a medical school dean this other thing of the convergence of engineering and medicine. There was political pressure to really, at that time, many of you remember, because it was one of the ideas at the Urbana campus, and they've done a great job starting a medical school solely focused on this. And we said, we are not opposed to that. In fact, we're the same. And we got a lot of support. And in my previous work, I had been doing a lot of research on lasers and so on. So I remained connected to physics and chemistry and math. And so the transition was very easy. And I had this device that was, as I mentioned earlier today, that Verily mentioned on their website about the success of the product. It had been 20 years in the making. I had the first maybe 10 patents on the concept, and 7 of the 10 expired before there was a product. So I don't get anything except 7 lines on my CV. But the idea of seeing something becoming, it's not ready for patient use yet. Could be a few more years, but still seeing that going forward was really very nice. Thank you, Sam.
One of the questions, Dimitri, is comparing your life in industry versus academia. Do you want to make any comments on moving back and forth?
It is not much different because, my approach has been you always find the smartest people around you. You encourage them, you empower them, you give them an opportunity to come up with to ask questions, to come up with solutions. I have no problem interrupting, giving my own solution. And I say, but I'm sure we're going to do better than this proposal. This new company that we spun out was formed on, I came up with over time about 50 different ideas that we can apply these. I mean, this is only in the eye. Imagine in the body, there can be 500,000 probably. And we narrowed them down with the help of the business people. Some of the ideas I loved most, we find out there's no market for them because they're interesting. And vice versa. Some things I said, this is not so important. We are finding this may be the best seller. So you have to have the humility of wanting to share your ideas with others and recognizing the moment you publish something, it's no longer yours. It is now shared with the community, and you surround yourself by smarter people, and miracles happen. Administration is straightforward. I tell you one thing I learned in academia, and now I'm applying very well in industry, is that you are not a firefighter. Yes, you have to have this fire extinguisher, but you have to know which fire is going to die on its own and which fire is next to a gas tank, and go handle that fire. Because if otherwise you spend your time just dealing from one fire to another. And I've seen in academia and in industry, many people get distracted by these, fire alarms that are going around. Miri Kochi, you've done a great job, and it's good to hear from you again. This is becoming a journey here. Yassine Chang, would you be willing to talk a bit about advantages of academia and research and industry? I had not, at the industry side in research, I came because of my previous experience relatively high up as an advisor to the CEO of the company. And later I came up with ideas and we spun a new company. But I think at the end, it's humility about knowing that there are many, many ideas out there. And the fact you have an idea doesn't mean anything. It's the energy that the teams that work on the idea to make it a reality. That's the key thing in my mind. There is more emphasis on rules and regulations about getting approval, about getting the product. But when I started talking with various engineers, I had to tell them science first. I mean, it's like, if, for example, if you have an idea and you think their scientific basis is weak, but you think there's a lot of money coming at the end, sorry, I'm not interested. I'm more interested in something that we can have, that the scientific basis is very sound in my mind and the likelihood of success is high, even though the market may be small. That's the thing that I brought with me from academia going forward. And you find out in academia, of course, there are many researchers, but in industry, there's equally good researchers, except maybe it selects those people who don't like to write papers or grants. So when I want to punish somebody, ask them to write. That's what happens in industry.
Dimitri, Jessica is an MD PhD student. She wanted to ask you a question about your hemoglobin A1C, if you can see it in the chat. I just wanted to bring that.
Jessica, I miss Jessica. Hi, Jessica. Yes, Jessica Lee. Just want to check, did you say there was a possibility? No, it's not determining. The question is there a possibility of determining certain lab value from an AI analysis of the fundus? I don't think it's determination as much as association. So what they did in the program, they had the data about hemoglobin A1C, and they fed it into the program in that particular population of, I think, 50,000 or 20,000 patients. And then over time, the program started learning by looking at the retina of guessing roughly what the hemoglobin A1C is. So in that path, yes, the program looking any part, if you feed the important data, then the program will learn. And now I'm interested more in seeing what is it in that thing that it looked at that could create the association. That we don't know. But it could be something about the shape of the vessels or some pattern that the program is recognizing. Would this be an additional tool, like a screening tool? Yes, very, very importantly. Meaning you may have a diabetic and you look at their eye and they've been trying to take care, but they didn't take that information. It can get you roughly, hey, this seems to be very high. Let's take it now. Or it seems to be under control. I don't think we can go to the point of actual determination, but guiding referrals, I think we are there.
As a nephrologist,
yeah.
As a nephrologist, when I was training, I was taught that the only place you can really look at a vessel is in the eye.
Indeed, yeah, at that time, and again, you learn a lot about the kidney by looking at the retina. I mean, it's,
exactly. We were taught
diseases are, especially in diabetes, for example, in patients. So of course, when you go to these big numbers and you say 90% or 95%, the remaining 5% are real patients who you may be misdiagnosing. So that's why I'm saying that there is an error. But we are at the beginning of a long journey. This is not the end. As Churchill said, it's not even the beginning of the end, but it is perhaps the end of the beginning.
Dimitri, thank you. I don't want to end. David is running this, but Colin Gallagher is one of our second-year residents, and he's asking a very specific question because you've excited him clearly and wants to know what can he do. I'm paraphrasing. Can you see his question?
Yeah, I'm seeing it now. Thank you, Colin. For some of us who have less formal training, schooling in these areas, other than that, what skills do you consider to be most important? I don't know how to code. I don't know much. I mean, I learned data science on business. I mean, business school is, if you want to just learn, lifelong learning is a great thing. I mean, I want to take as many courses as I can, but mostly to learn. If I apply the skills I learned in business school to run a business on my own, I will fail, because I was learning it for self-actualization much more than as a practical skill to make me do my work. So learning along the way will be good. But the best method, I think, is being surrounded. You find the best possible team you can associate your time with. You have discussions. you expose your ignorance with great humility. Say, I think it's this, but, and then they are all laughing at you around. This is a good learning moment for you. And you should not be discouraged when you notice everybody knows the answer except you. That's the place. I mean, which means the delta is so huge that this is a great learning opportunity. But if you know all the answers, you're not learning anything. But what are technical? I mean, you can take courses. There are many books on AI. I mean, if you're interested in the field, you'll find reading papers, but associating yourself with many people. I tell you, the School of Bioengineering, which is reporting jointly to the College of Medicine and Engineering, they have great strength in these areas that have been untapped by members of the College of Medicine. So you can go put AI, for example, if you're interested, Colin, and put biomedical engineering, and you'll find names of 10 different research, see what they're doing. Say, I'm thinking of this, can you help me? You talk to a few of them, and all of a sudden you've created a great area. But nothing beats the basic question. What is the research question you're trying to answer? That's how you learn, rather than saying, what skill do I learn? And now I'm a carpenter, where's a nail that I can go and hammer? That doesn't work. It's better to say, I want to solve a problem. And then you see who's the best person to work with to solve this problem, and you learn along the way. Sorry for those of you who are as seasoned or more seasoned than me, you feel that I'm stating the obvious.
David,
So
I just want to make sure Vanitha had her question, so you could ask
Okay,
that.
Vanitha.
Go ahead.
What do you
She's an
think
IMED
the barriers to innovation being adopted by the mainstream health system, and how to get about combating them? I think the healthcare system, the innovations, by the way, this is an area I paid a lot of attention to when I was dean, but I wasn't able to make inroads because there were smarter people paying more attention to it. And I was mostly attracted to this, basic science, pharmacology aspect, and the bioengineering, let's call it, or microelectronics. But there were at the same time many people making great inroads in innovation about how to change the healthcare system. That's a great question, and the difficulties of solving it have been great, including politics, etc. But designing a system that will identifying a problem in the healthcare delivery science is extremely important. There are programs, including the most known ones are Harvard and in New Hampshire at, sorry, I'm blanking, Dartmouth. They have probably some of the most rigorous healthcare delivery science programs, meaning, and I was going to start a program like that when I was dean of the medical school, but it was going to be, the cost was going to be high and the uptake was going to be small. And given that there were these other programs were not able to fill, even though, because they were targeting, people with the seasoned experience in healthcare delivery science and adding the formality. This is a good area to change the system, if that's your question. But if the question is, how does the system prevent you from innovating in science, in medicine, in AI? There are no barriers there. I think it is just a personal interest that will be a barrier. But in changing the system itself, there needs to be great innovations. It's like science. I mean, it's a problem. It's a disease. Like same way you have a patient with a disease. Our healthcare delivery system has a disease. Many people have focused on the value-based approach, etc. But when I hear people talking about them, it's a cliche here and there. I always spend part of my time thinking of how can we solve this, but I'm now getting more and more far away from it, unfortunately, and I'm not smart enough to be able to solve it.
So neural networks are obviously incredibly powerful, but to understand the underlying mechanisms of the biology, it would be helpful if we could solve the black box dilemma. So do you have any thoughts on how to address?
Yeah, I do. I mean, it's easier if you see the capabilities, they can give you the answer. Let's take the hemoglobin A1C. Supposing we did that, you can go and ask the program. Now, it's not hidden. It is hidden from a casual observer. It is open to anybody who wants to read the code, but very few people can do that. But you can ask something in between. Show me what are the main areas that you've given, or allocate certain percentage weights for following things. And you may then develop a hypothesis, for example, that it could be that it is the vessels, maybe the hemoglobin, or it could be some other factor that's related to diabetes that has affected the hemoglobin A1C to change the reflection coming out of the vessel, right? It could be the diameter of the vessel. It could be the branching at certain intermediate or capillary level. We don't know that unless you go and probe and make it your research effort is to dig now about something less interesting. The most interesting part that was published, it can be done. Now the question of why is very, very interesting and requires somebody to dedicate part of their life, part of their career, just to answer that question. And then it may lead us to some other finding outside the retina that can help us in management of diabetes, for example. It could be kidney failure. But how you arrive at it has to be is the why question. Now we have, I mean, we've trained, especially in medical school, the tests are always about the what. What is this? What is that? Or what's the diagnosis, etc. And I have been long pushing to abandon the what. I mean, it's necessary for exams, for training, for certification, and go into the more inquisitive why. Pourquoi?
Dimitri, to build on that question, the why question, isn't that the biggest challenge for artificial intelligence, to move from associations to causality? And do you see developments in the AI field, in the medical AI field, that is moving into developing sophisticated ways to develop causality analysis? So like you suggested, weights might be one way to do it. In genetics, we do Mendelian randomization that is getting us closer to causality. Do you see something similar in image analysis and in linking image analysis to biological parameters?
What a great question. I really don't know the answer, but it's a very intriguing question, and I think it's very appropriate. You know, I was thinking along a different path, but your question now makes me think that maybe rather than accepting that this is the image that you get and then you analyze it and try to now probe something and test it with other associations, you make the program itself even more intelligent that doesn't answer the what question, but also answers the why question. I'm sure some very sophisticated programmers are thinking about that. I have not researched it, so I don't, do you know of any? I'm sure you, I mean, because we can learn. AI, by the way, thank you for your question, also illustrates that we're copying from the big data that came from basic science, actually, and applying it now to clinical science.
I do bring it up because there's a person. No, Pearl is an AI expert. Sorry.
Yeah, no, I'm not an AI expert. I know about potential applications. But this is a great way, and we'll talk to many AI experts to see if they can reanalyze the data in a way. I mean, you can state a hypothesis and test it, but the capabilities are so huge that, you know, these things that you wouldn't have imagined. Like it's a joke to really know whether somebody is a smoker just by having a picture that the eye doctor is looking and calling normal. I mean, that's what we said. These images look normal, but they contain so much more information. I mean, we are at a stage like we talked the genetic analysis that you used to look. I mean, when I was a medical student, they would do the genetic analysis would look to see if there is trisomy or no. And they say, no, you have 26, or there is no trisomy here. And so it's called normal. But we know these genes are not all normal. They look normal just when you put them on that old-fashioned system. But once you started understanding what's inside every, you know, the code, the knowledge became much better.
Well, that was a lot of good questions, good answers, and we appreciate your great talk. I see hands clapping and in the background.
Well,
it took us a long time to get this all organized, but it was worth it, and we're so glad you could make it. And we're looking forward to having you come back.
Thank you. I'm here in Chicago. I'm at home. I'm not too far.
Well, that's good too.
Yeah, exactly. So,
Thank
I
you,
mean,
Dimitri. Happy Thanksgiving.
thank you all. Yeah. Happy Thanksgiving to everybody.
Happy Thanksgiving to
Stay
you.
safe.
Thank
Stay
you so
safe.
much,
Stay safe.
Dimitri.